Well, hello friends. Today we are going to look at a performance issue because I got this comment from Buzz here, and it's about on the video where I port Git to Serenity, and he says that he notices a performance issue when I'm running Git, and how on a Linux machine the Git commands return instantly, but inside Serenity it takes a second or two. So what's the reason for this? And do I think I'll be able to reduce those running times to acceptable numbers? If so, how? So I definitely think so. And today we will see if we can get it done. And I'll show you how. So first off, let's just look at the problem. So if we go into the Serenity Git repository here inside Serenity and we run git status, we can see that it takes quite some time to run. What was that? 4.395 seconds. That's a long time. And then if we run it again, now caches are filled with disk blocks and stuff, so then it's about 2.2 seconds. We can also run with time in Serenity. I don't have to look at the debug output. But 2.1, 2.2 seconds, say. And then if we run it here on my Linux machine, it completes in 0.01 seconds. So that's a heck of a lot faster. Now, since I'm not sure what the performance problems are going to be, we are just going to aim for some kind of improvement, but I think we should be able to at least cut it in half, probably more. We'll see what comes up, but given how much lower this is, I imagine that it's something pretty fixable. So I spent some time this morning working on the profiling tools in Serenity to prepare for being able to analyze this stuff. So now it's actually possible to run the profiler like this, ls/bin, and what this does is that it gives you a profile that you can open in proc profile. And this is the total execution profile of the ls program that I just ran. And previously this was not possible. You can only attach to an already running program, but now you can use the profile command to profile the entire lifetime of a command. So this will be very useful. So with that in mind, let's profile. So we'll do git status. And there we go. And then I run the profile viewer as root because that allows me to also symbolicate kernel functions. Okay. So this is the entire git status command, and we sample it 1 time per second. Oh, no, 1 time every millisecond. So 1,000 samples per second, which means that in this case, we don't have symbols for the Git program because we strip it, but we can see that a ton of time is spent in the kernel anyway. So blue thingies are user space stack frames, and red thingies are kernel stack frames. Maybe it would be better to maybe we should make a build so that we can see what it's doing in user space actually. So let me just turn off stripping, and we can rebuild Git, and then oh shit, I have to actually make. Okay, we'll try that again. And I know that this is going to take up a ton of space, so I'm just going to make some space for it in my disk image here. Instead of 600, I'm going to do disk size is, I don't know, 2,500? Because Git installs like many 15 megabyte executables if you don't strip them. So we're going to need a lot of space. But having the space will allow us to see what it's doing in the Git program. Although I suspect that Git is probably fairly optimized given how popular it is, right? So most of the performance problems are going to be on our side. But it's still interesting to see what it is that they're doing in the Git program. All right, come on now. One of these days I'm going to get one of those thread rippers, maybe. One of these days. We'll see. I keep saying that it would be nice to get a faster computer, and I'm really looking forward to being in a place where I can do that without worrying about finances, but at the moment I am laying low. So let's try this now. Let's see if we can. Come on now. All right. I wonder how much space we have. Still some available. So let's go here, and I think we'll do a dry run just to warm up the disk cache, because I don't care so much about the uncached case anyway. But after this, we'll do like that. This shenanigans here we can ignore. It's just the profiling code whining. Okay, so now we have user space symbols, and it's a little bit of a mess, but it would appear that we are in blob.c, whatever that means, and we're doing something called refresh cache int, and that seems to be by far the biggest thing that we do, that we spend time on. So 1.256 seconds are spent in this function, and we have almost a whole second in something, which is doing git open clo exec, which is doing open, which calls the open syscall. So we have a basically it looks like time is spread between the stat syscall and the open syscall, because if you look at these two combined, you have 1.2 second and 0.8 seconds roughly, and added together it's over 2 seconds, right? So the majority of the runtime is spent either doing open or stat. Okay, so that's useful, and I guess we can look at stat first, although maybe if we open them up further we can see that both of them actually spend the majority of their time in path resolution. Stat spends basically all of its time in path resolution, and open spends the majority of it in path resolution, but then also a bunch in file description create. So I think if we look at path resolution, we'll probably learn more here. Okay, so let's just drill into it. So path resolution, I guess probably what Git is doing is, if we look at the contents of a Git repository, then you have all of these objects here in these objects directory, and I'm assuming that we're just traversing this whole thing and statting everything. At least we're statting something a lot. And so it would make sense that we have to do path resolution, because when you call stat, you're just passing in a path, right? And then we have to take that path and turn it into an inode that we can read from to get the metadata that you want for stat. So we are in ext2 file system lookup, populate the lookup cache, and the lookup cache, and then we walk the directory and then add everything in the directory to a hash map. So the way that this works is, if you look at the inode class here in the ext2fs, every inode has a lookup cache. It seems like maybe I'm in user space mode. No? Redefinition. Wait, what's going on here? Undefined template. Why is it not doing the right thing? Okay, I don't know why that was red. Had to placate QCrater a little bit. Anyway, so the lookup cache, it's a per inode cache that is only used for directory inodes. So basically, if an inode represents a directory, then the first time you try to traverse that directory or look for some file in that directory, then we will traverse the entire thing and then find all of the file names contained in that directory and put them into this hash map, and that's the lookup cache. And so the lookup cache maps from a file name in a directory to an inode index. And this is how we are able to go very quickly from sort of a directory and a name to a child inode index. And what we're seeing here is actually that during path lookup or path resolution, we are doing a heck of a lot of populating these lookup caches. And basically, we're doing a bunch of lookups, but most of the time we have to populate because I guess we invalidated the cache or we just got rid of the inode because we had too many or something. Who knows? We had to, at least we have to repopulate the lookup cache, and it seems expensive. And the price that we're paying appears to be related to the hash map itself, because this is hash map set. So if we look at populate lookup cache, we can see here that we're traversing the directory, and we call children.set for every entry in the directory, and that's just this hash map right here. So hash map set, it's very heavy. And I guess it's just a hash map itself that's heavy, and then we also have a fair amount of time spent in creating strings, actually. So it would be interesting to turn the profile around and see. Okay, so now I inverted it using the invert tree option, which just flips the tree upside down so that the innermost stack frame of each sample is used as the root of each subtree. So here we can see that the most popular innermost stack frame is string impl create uninitialized. And most of it comes from custody and path resolution. So we're spending a huge amount of the runtime just creating strings and also creating custody. And this is the hash map, putting stuff into hash maps, right? Yeah, it's hash map set. So the hash map in Serenity in ACK right now is as a bunch of buckets, and each bucket is a singly linked list. And so that's why we're seeing singly linked list here, because every bucket in the hash map is a singly linked list. So it looks like we're spending a fair amount of time just creating these, or appending something to a singly linked list. So singly linked list, append, we'll do a new node, right? So my guess is that all of this is allocation, because create uninitialized, if we look at string impl create uninitialized, it calls new. Or rather, this is a placement new. It calls kmalloc, sorry. Custody create. Create, where is create? Right here, calls new. And file description create, like, it's going to be the same thing in all these. These are all memory allocation. So it seems like we could probably do well here with optimizing allocation somehow. And the reason that we don't see the allocator, by the way, is because in the kernel, when we call the allocator, then the first thing he does is turns off interrupts, and the profiler relies on interrupts to be able to sample the running thread. And so if you turn off interrupts, we cannot get any samples of what it's doing, so we just have no idea what's going on. But we can make an educated guess here that because we're always like in something that would do an allocation next, then it's probably safe to assume that it's doing that. So all of these guys are calling kmalloc, at least the top 4 innermost frames. And kmalloc is not fast, we know that. So kmalloc is a first, I can show you, it's a first fit allocator, and it has a hard-coded base address, and it's 3 megabyte total of pool, and it starts at the 4 megabyte mark into the kernel address space, and then it goes 3 megabytes from there, so it ends at the 7 megabyte mark. And it's divided into 8 byte chunks, and each chunk is represented by a bit here in the alloc map. So the alloc map is just a bitmap that has 1 bit for each chunk, so we know whether or not a chunk is allocated, and then when you call kmalloc, it will scan this alloc map until it finds a long enough sequence of zeros that it could fit what you're trying to allocate. And so right now, that's potentially almost 50,000 bytes of map that you would have to scan. So one thing that we could try here is we could just increase the chunk size, and then try again. Because if we double the chunk size, that means that the smallest amount you can allocate from kmalloc is now 16 bytes, but it also means that the alloc map is now only 25,000 bytes, which means that we have half the amount of bits to scan when we are looking for a slot. So let's try that. Okay, so 900 milliseconds, that's already a pretty good improvement. Let's see if that's reproducible. Yeah, that's really good. Okay, so let's get a profile of that now, see what it looks like with that change. So we flip it upside down. Now we are looking at still the most popular innermost frame is still string create uninitialized, but it's significantly less than before. So this made allocation a lot cheaper. That's really good. So the downside of this change is that now whenever you allocate 4 bytes, you still get 16 bytes. When you allocate 8 bytes, you would previously get 8 bytes, but now we're going to give you 16 instead. So that's a little bit of a downside to that, but I think it would be fine to make this change because it was 8. Previously it was 8 because we were really tight on kmalloc space, but this was back when we only had 1 megabyte total of kmalloc memory. I've since increased it to 3 megabytes, so the pool size here used to be 1 megabyte, but now it's actually 3, and we could probably increase that again a little bit. But we have 3 times more memory now than we did before, so I think we could increase the chunk size even to 32 if we wanted to, and see if that buys us any more. 667. Okay, that's pretty good. Look at that. It makes you wonder if we could go even faster with even bigger chunks. Of course, there's going to come a point where, like, you're giving up too much. Oh, what the heck? You're giving up too much slack in each allocation, and you're wasting too much memory. But just in the interest of how much more can we buy using this trickery? 521, 598. It's all right. Okay, so now we're starting to get like diminishing returns, right? So I think 32 was pretty reasonable. We were 550 something. between 550 and 600. 500 is something with 64. Get status. Actually, it's another 100 milliseconds if we go down that much more. But I think it's a bit too much for comfort. But we can go to 32, because 32 is not an unreasonable amount of memory to give you when you ask for a heap allocation, I think. So that would be, I think we can do that change. Increase kmalloc chunk size from 8 bytes to 32 bytes. This gives a huge speed up and running git status in a Serenity OS repository checkout. Repository directory is the same. Most of the time was spent allocating strings. What else can we do? So I guess another thing we could play with is we have sanitize kmalloc here. So this is a thing that we always turn this on right now, which is that whenever you malloc something in the kernel, then we will scrub it out. We will like memset it before returning it to you. So we'll replace everything with BB. And when you k-free something, we'll replace everything with AA. And I do think that it would be interesting to see how much that does. If it does much. It's about the same, I guess. I guess I would have expected that to do a little bit more, but then we don't have to turn that off. At least that's a good thing. So let's get a new profile. Profile, let's see, get status. All right, so turn that around. And now string impl creation is not even at the top anymore. That's pretty neat. So what do we have here? K result. What? Why is that even at the top? Did I not sync? Oh shit, I did not sync. That means that the symbols in the kernel are, they're not matching up. So the profile viewer depends on having synchronized symbols with the kernel. So let's try one more time. This workflow is really, really pleasant. Just profile it and open it in profile viewer and then see what's going on. Okay, so string creation and then custody create and these hash maps. Region remapping. What if we turn it around like this? Stat is still by far what dominates the runtime. It's a fair amount of time spent in split view. Custody creation, we spend the time doing string allocation. Maybe we can be smarter here. So the kernel has two allocators, and kmalloc is the default allocator, but if you know that your object is just going to be of a certain size, then you can use the slab allocator, which has pre-allocated slab storages for 8-byte, 16-byte, 32-byte, and 48-byte objects. And for custody, we could probably just make it slab allocated, because what was it, 32 bytes? It would fit perfectly into the slab, actually. So if we do that, the benefit of the slab allocator is that you don't have to scan the kmalloc bitmap to find a slot. You just pop the next available slot from the slab allocator's free list. So it's like allocating from slab allocators instant. And it's really, really good in this case, because it seems like we are spending a lot of time allocating these. So maybe we can do much less of it. And it's as easy as just doing this. This macro, what it does is just replaces operator new and delete for your class to call slab alloc and slab dealloc. It takes care of everything for you. Let's see. Okay. So custody allocation is, where did it even go? It's all the way down here. Okay, that's good. So we got it way, way out of the top functions. That's really good. Then maybe we can do the same for file description, because that's another object that I think is relatively small. File description is 64 bytes. So our biggest slab allocator at the moment uses 48-byte slots, but that's not going to fit file description because it's 64 bytes. But what if we just made these things into bit fields? Nobody would care. And we should be able to shrink the class quite a bit by doing that. Let's see how much that helps. 60 bytes. Okay, well, doesn't solve everything, but we can put the lock up here. And how big is this guy? 1 byte. What if you would be... How many options does this thing have? FIFO, direction, 3 options. So it can be a 2-bit field. Still 60. Dang it. How big is the lock? Lock is pretty big. Optional is 8 bytes. Maybe that's not very good. Inheriting from ref counted, which is how big? 4 bytes. That's a bit annoying. Does it matter how we put these? Maybe it doesn't matter. No. Well, anyways. Actually, I could use PA hole on this thing. I can't use a... it's too small to blah, blah, blah. What if we use 3 then? Unsigned. Set FIFO direction, blah, blah, blah. I just want to try it. I mean, actually, I just want to get PA hole working because I need to compile it and then I can run PA hole and then see what's going on. All right, hurry up now. Another option, of course, would be to make the slab size slightly bigger. It wouldn't be the end of the world if we made it 64 bytes. So what do I say now? PA hole class file description kernel. Okay. So we have 3 bytes of padding after the optional. Interesting. So maybe we could slip all of these guys into there. Could we do that? What if we put all these guys after the optional? I forget if that works or not. I know it works if it's your base class, but I don't know if you can put them after a member like that. It's been too long since I was messing with struct packing. It's really sad to have all that padding in your class, and you don't care anyway. Yeah, we can't get out of it. Shit. 24 bits whole. Well, I can't do much about that, too. File flags. Anyway, I think we'll abandon reorganizing this struct, and we will instead simply change the size of the slab and the slab allocator. So I'll just take the 48 slab and make it into 64 exactly. Okay, will that just work? See if we can get that. Wait, I forgot to make the change to file description. It'd be interesting if we could just get allocation out of the hop path here. It's funny, like, I know that kmalloc is quite bad, but it's not quite bad enough that I want to spend time on replacing it, so I'm always just fixing things up around it instead. And feels like maybe we can get away with it one more time here. Well, one day we're going to replace it with some different allocator that doesn't have that 3 megabyte limit, and that would be good. But right now, it's a limitation that maybe we can survive. So, PV proc profile, flip it around, and file description create is gone as well. Where did you go? No, that's read. File description destructor. Oh wait, it's right here. Okay, it's not gone, but it's very small and tiny. It's not so bad. Maybe he's doing something heavy. What are we doing there? We call new, but that's a slab allocation. But we call inode file create also, which is new inode file. So we're creating a file to wrap the custody that we are passed. But now we're talking pretty small things here. Although I suppose we could try to make inode file be slab allocated as well, but because now like one big thing here is like reading blocks from the disk file system. It's the biggest thing now that we spend time in, and then string allocation is the second biggest. And we could definitely get improvement here by like doing less string allocation by making path resolution use a cache for the paths, for example, so that like once you've resolved like your home directory .git, then we wouldn't have to like re-resolve that every time and recreate new custody objects and stuff. But that's a bigger change, and I'm looking for little tweaks here because the point of the video is to just do very targeted performance optimization to fix a specific problem. So I think we'll do the custody change. Kernel make the custody slab allocated. And I don't want this change right here because it's irrelevant. Is it any faster now, by the way? I forgot to check. .8, 6, 11. Well, it's in a pretty good place. 5.9. Yeah. So we're peeking under into the 5s. That's good. So let's do the slab allocator change. We can live with this. It gives us a little more breathing room in the other objects that use a bit more memory anyway. Also, I'm not quite sure about that 8-byte slab size anyway. I wonder if anything's actually using it. Make slab. We can actually find out because we know everyone who's slab allocated. So this guy is 40 bytes. This guy is 12 bytes. And this guy here is known to be 64, and custody finally is 32 bytes. So we are totally not using the 8-byte slab allocator anyway. We're reserving 384 kilobytes for it. So we can just get rid of that. And that's cool. Don't need it. And what else do we want to do? I guess we don't have to do anything for that, really. Does that just compile? Things just work anyway, yeah, as expected. So I guess we could actually take that space and put it into here. Now that we threw away that much, we'll give him 0.5 megabyte. We don't have to worry too much about that. I have to reorganize this at some point, but it does seem pretty okay. Just to confirm that we're still good. Yeah, we're still good. Status, so kernel, move 8-byte slab size and increase 48 slab size, 64 byte. Say tweak slab allocator slab sizes. Nobody was using the 8-byte slab size, so get rid of it and move all of its capacity to the new 64-byte slab size, which replaces 48 Okay, we'll make that change. So kernel make file description slab allocated. So the more things we slab allocate, the better. It's kind of strange that the sanitizing stuff didn't have any effect. I wonder if that's really... Because I feel like, why wouldn't it take time? Maybe these allocations are so small anyway that it doesn't matter. But if we're doing so many of them, you would think that it would matter. But this is that like instinct and intuition fucking with me, because like the profiler tells the truth, right? It's just sampling the process every so often, so it tells me what's actually happening. Yet I still want to go and think that like, well, calling memsat should take time. It's just what I believe, but it doesn't matter what I believe really. What matters is what it's actually doing. So if we profile, see get status, we can probably see that it looks just the same. So it doesn't matter if I have this on or off. Interesting. So maybe we're going to be happy with what we've achieved here, because we went from like, what, 2 seconds to half a second? I'd say that's a really good improvement. And obviously on Linux, it's completely instantaneous, but in order to achieve that, I think we're going to need a bit more work. We're going to need to implement some caching, path lookup, path resolution caching. And what else is slow? Directory traversal is not super slow. Copying string from user. We do spend some time copying the string arguments from user space into a kernel buffer. And we could definitely do that without a heap allocation if we wanted to. So that might be an interesting option. And also the hash maps. We could do hash maps that don't have a sort of a disjointed singly linked list with individual heap allocations per node. That might be a better way to implement hash maps. Like we could do open hashing, for example, which would cut down on the amount of individual heap allocations. But this like messing around with data structures, and that can be done separately. And then the fact that it just soaks up a lot of time just reading from the files. There's probably some smart thing we can do here as well. I imagine that like currently we are reading, I think, up to 4 kilobytes at a time from disk. And we could definitely do better with that if we learn how to read ahead and stuff like that. So in fact, that's probably something where we could gain a lot if we get smarter about read ahead. Because currently we don't do any read ahead. We just only read whatever you're trying to access at the moment. It's funny, I didn't even look into read block here at first. I was just fixating on the allocation stuff. But yeah, read block. I think read ahead. And you could imagine that when you start doing like sequential reading on a file descriptor, then we would not only read like the one thing that you're accessing, but we would also like cache a couple of blocks forward or whatever. I don't know, something. That would be interesting to get into, but I think maybe we're going to be happy with what we have here. So I'm pretty pleased. Did I have any more changes to make? We don't need the kmalloc change. I don't know why this one was needed in QCreator. So Anyways, pretty good improvement, and I'm glad I could show you the new profiling workflow. So you just use profile-c and then the command, and then you can pv proc profile. And if you pv as root, then it will show you the kernel symbols as well. Actually, let me show you what happens if you don't pv as root. Then it will look like this. And you don't know what the red symbols are. You just know that it's somewhere in the kernel, but you don't know what. But only root is allowed to know. So, yeah. Okay. Anyways, I think that's going to be the end of the video. So, boss, I hope that this gives you an idea of how I would approach this problem of making things faster. And of course, it needs to be approached more, but it's just more of the same, like profiling, figuring out what's slow, coming up with some way to make it less slow, and then reprofiling, figuring out what's slow now, doing it over and over and over again, iterating like that until you reach the target that you have in mind. So yeah, thanks everyone for watching and for hanging out. I hope you saw something interesting, and I will see you next time. Bye.